Our session begins with the talk on laser plate. It's a pleasure to introduce Jessie Zhang, who's a postdoc in Holger Mueller Group at University of California, Berkeley, and she's working on development of the very much anticipated laser faceplate.
Cool. Hi, everyone. Thanks for the introduction. And I'd like to thank the organizers for the invitation. I'm really excited to share our development on the laser faceplate at UC Berkeley, both in single particle analysis and tomography. And so shown here are two images. One is apoferritin in a SPA sample, and this is a slice of a tomogram, both taken with a laser faceplate. So we all know cryo-EM is developing really rapidly, whether in SPA, where we're really going for smaller, more complex proteins and ever higher resolutions, or in tomography, where really trying to understand these biological samples in their native cellular context. And as we know, a fundamental challenge in most of cryo-EM is radiation damage from the electrons. And in particular, the low electron dose limits the signal to noise ratio we can obtain in these images. And earlier this morning, we heard two talks discussing software approaches where we can try to get as much information as possible from these noisy images. There are also hardware approaches to addressing this challenge. So for example, better detectors to get better signal to noise ratio, or going to lower voltages or liquid helium temperatures to try to minimize the radiation damage to begin with, or this idea of faceplates to improve the contrast in the images themselves, and many others. And so what I'll be talking about is developing faceplates to address this challenge. So first, a little bit of theoretical background. So in transmission electron microscopy, we have an electron beam that interacts with a specimen. These biomolecules interact weakly with the electron beam and imparts a small phase shift on this beam. And you can view them as an unscattered part and a scattered part, shown in purple and orange here. When we detect this electron beam at the detector, however, we measure the amplitude and we're left with actually no contrast at all, even though there is this phase shift. And conventional cryo-EM deals with this by applying a defocus, which distorts the wavefront of the beam and allows us to get a contrast, but with some compromises. Now, if we look at these two beam paths, we notice that the unscattered part and the scattered part are actually spatially separated in the diffraction plane. The unscattered part focuses in the diffraction plane and offers us an opportunity to tune their phases separately with the faceplate. So if we had some object or means of phase shifting this unscattered beam by exactly 90 degrees, then when we measure on the detector, we actually can observe a contrast. So this is phase contrast microscopy and has been known, is really well known and well established in optical microscopy for almost 100 years, but it's experimentally challenging in electron microscopy, mainly due to whatever you put in the path of the electrons will interact with the electrons. So our approach is to use a laser to phase shift the electrons. So the laser can create a phase shift through what is known as a ponderomotive potential. And using a laser is nice because it's not a physical, tangible material you put in the electron beam, and so there's no charging. And so you can end up with a very stable phase shift. And lasers are very well controllable, and so this provides a controllable and stable faceplate. One of the challenges is that it needs a very high power, so on the order of 80 kilowatts. And just to give some context, so the highest power industrial lasers you can get are roughly 10 kilowatts. So we need almost an order of magnitude higher than what is offered. And so our approach is to amplify light using what is known as a cavity. It's essentially two mirrors, and we can send some light in. That light bounces back and forth, and it builds up within this space. And we end up with a very intense spot right at the point of the electrons. A slightly more detailed schematic. As I shown before, so the electron beam interacts with the specimen. The unscattered portion focuses at the diffraction or back focal plane. But in normal microscopes, due to geometric constraints, it's actually very difficult to insert a laser faceplate in this plane. So we need transfer optics to magnify this back focal plane for us to insert this cavity. And I'll come back to this point in a bit, but the presence of these transfer optics sort of increases the aberrations in the system. And that's something to make note of. Within this cavity, the laser beam bounces back and forth and you form these sort of pancake structures. And the electron beam needs to be aligned right at a high intensity spot. So one of these bright spots to be able to get this phase contrast. So assuming that's all well aligned, the CTF looks something like this. So this is your normal defocus spaced CTF. With the laser faceplate on, you see that the low frequency information is boosted by a lot. At high frequency information, assuming we still apply some defocus, we still have these oscillations. And at high frequency, we're still limited by the coherence envelope, which is determined by chromatic and spherical aberrations in the system. So that's enough theory for now. How does it look like in the lab? So this is what we call this microscope the Titan in our lab. And it's really been our development microscope that we've been working on over the years, where we've prototyped faceplates and tested them in this system. It's a low base Titan with a side entry holder. And the transfer lens module is here where we can insert the faceplate. And these are the surrounding optics and control electronics and software that we use to control the lasers. And you may note that these spherical and chromatic aberration numbers are quite a bit larger than what you may be familiar with in a standard instrument. And that's due to the transfer lens system. So what actually goes into the microscope looks something like this. You sort of stick this onto a flange on the microscope. The laser beam comes in like this and interacts with the electron beam through a hole coming down this way in the column. And a good chunk of all the data I'm going to be showing today was performed on this instrument, where we were really just testing that the faceplate works and developing the protocols. So previously we have developed a workflow for SPA where it's fully automated and we can reliably get 90-degree phase shifts. In particular, so on top of all the hole alignment autofocusing steps, the electron beam needs to be aligned to the laser beam for every acquisition that we take. So the unscattered beam needs to be exactly aligned with one of those pancakes I was talking about earlier. And we use those, we do that by using some deflectors before the faceplate. And we can visualize where we are aligned to by pulling some defocus. And this is actually imaging the laser light using the electrons. And with an image like this, we can know where along this laser beam we are aligned. So using this protocol, we can routinely achieve phase shift stabilities of ± 10 degrees. And we actually think that a lot of this comes from the uncertainty in the fitting rather than stability of the system in itself. And this can operate for hours without any human intervention. So here's an example of some images taken on our Titan of apoferritin and a comparison of the laser on and off data. And thanks to Stephen for the shout out yesterday, like on these laser on images, you can really just by eye tell a lot of the heterogeneity in the sample. We can perform 3D reconstruction using the laser faceplate. And here I show a B factor comparison between the laser on and laser off data on apoferritin. And in both cases, the transfer optics is on. And we observe a comparable B factor in this case for apoferritin, which is a fairly large particle. And we have observed similar results for Rubisco. And so this resolution I show here is by no means good in any sense. And we understand this as we're really just being limited by the aberrations in our microscope. So with the same sample, same microscope, if we turn the transfer optics off, we can actually get a much better B factor. So in this system, we were really limited by the aberrations in the microscope. So with that understanding, a few years ago, we obtained some funding from the Chan Zuckerberg Institute and bought a new Krios state-of-the-art microscope. And this comes with a cold FEG and all the automated autoloader systems, and also a CS corrector, along with an improved transfer lens module here, and sort of the standard Selectris Falcon setup. And so with a CS corrector, we can tune CS to be very small, and the chromatic aberrations are improved in this system, as well as we have a much smaller energy spread due to the cold FEG. So we signed off on this microscope about a month ago, and within that month, we have installed a new faceplate into the system. So this faceplate is similar to what I just showed you a few slides ago with some minor modifications. It's inserted into the microscope here, and these are optics, and controls are outside the box. And I'm really excited to share with you that as of 5 days ago, we have been producing phase contrast images on this new microscope. So this is, again, apoferritin just for characterizing our system, and a comparison of laser on, laser off. It's probably kind of difficult to tell just from this images how much better this microscope is compared to the Titan. So here I show a comparison of the CTFs, and you can really see that on Thea, the tone rings just go out much further, and we're not losing the high frequency information. So with this new instrument, we're really at a point where we can explore the full capabilities of the laser faceplate. One of the directions we're working towards is SPA of smaller proteins. So as we know, enhancing the signal to noise ratio at low frequencies allows us to see smaller proteins much easier. So this was, again, taken on the Titan microscope, and is myoglobin, which is only 17 kilodaltons. And with a 1 micron defocus and the laser on, we can easily identify these particles. Whereas with the laser off, even at 10 microns defocus, it's really hard to see these particles. So at the time, we also tried to go for a 3D reconstruction using the laser on data, but at the time it sort of eluded us, and we really think it was just because we were losing all the high frequency information in that microscope. So with this new microscope, we really think that we have the opportunity to look at smaller particles. And so one thing we have started taking data on in our new microscope is hemoglobin, which is slightly larger than myoglobin, but also considered not too big. And we're still working on processing that data. So stay tuned. This is fresh and hot off the press. Another direction that is possible with this new instrument is in-focus imaging. So in sort of conventional TEM, we get contrast by defocusing and a combination of spherical aberrations. In the presence of a faceplate and tuning the CS to 0, we can, in principle, eliminate the oscillations at high frequencies in the CTF. And that is nearly all the information that is carried by the electron beam and can be accessible by us. There are challenges. Experimentally, it's very difficult to accurately and precisely set the defocus in experiment. For one, there's sort of hysteresis from the lenses, and there's also, ice thickness and all that. And we really need to be down to tens of nanometers for this to work. We have made progress in precisely setting it. We have characterized the hysteresis in our system and can precisely set it. And we're still working on the accuracy. And part of the accuracy also comes from challenges in actually determining the defocus, because most CTF fitting, looks at tone rings. But if we look at when we're near focus, we actually don't get any tone rings at all. So this was, again, the myoglobin data set. We took some near focus, and we think is close to 50 nanometers. But without tone rings, it's actually really difficult to fit. And so we have some ideas here, either using, for example, 2D template matching, or from a 3D reconstruction, we can backtrack focus values. Okay. So that's sort of on the SPA side. In the next part of my talk, I'll switch gears a bit and talk about tomography. And tomography is really the next frontier. And so we're really excited to see how the laser faceplate can help with this. In tomography, there are sort of additional challenges, both even without the faceplate, there are additional challenges, and with the faceplate comes additional challenges that we need to address that I'll discuss. So one, we know that in tilted samples, the beam-induced motion becomes more apparent in the images due to just the projection of the doming effect. And we actually think that the laser faceplate can help in this case, because we can sort of fractionate the movies into finer frames to perform motion correction. So we've done some preliminary characterization where we compare motion correction with laser on and laser off. And we find that motion correction, even when fractionated down to 1/8 of an electron per angstrom squared per frame, we can still obtain smooth trajectories compared with laser off. And this one is actually sort of cherry picked in some sense. In some cases with the laser off, it actually fails to motion correct at all. So this is sort of one aspect where we think the laser faceplate really has an advantage. So on with tomography, we've developed a workflow that is also fully automated. So one thing we were kind of uncertain about is when we tilt the sample, how that would affect our laser alignment. And we've developed a protocol where still we can align the laser, align the electron beam to the laser at each tilt angle and reliably get 90 degrees within a tilt series. So from a tilt series, we can reconstruct a tomogram. So this is our first attempt at a tomogram, just on a sort of SPA sample of Rubisco. And you're looking at it going through Z slices in this movie. You can really see these particles sort of pop in and out. So this is really exciting. This really allows us to see these particles really nice. And with the faceplate, we can reliably reconstruct these tomograms. One point I would like to mention, though, is you may be wondering what these black spots and white spots are. So these black spots are actually the gold fiducials in our samples. One point is that we actually think we don't need these gold fiducials, even though it is sort of standard practice. But with the laser faceplate, we can do tilt series alignment even without the gold fiducials. But here it's actually a nice demonstration of a phenomenon that is relevant to the laser faceplate, which is ghost images. So if I zoom in over here, and we just look at this Z slice, so the actual gold fiducial is actually these black spots in the middle that come in here. But what we're seeing on the sides are sort of like they're twin images, and they're ghosts formed by the laser faceplate. So what's happening is that the laser acts as a diffraction grating to the electron beam. And so it gets diffracted, and in the imaging plane that we see, it forms ghost images that are a fixed distance apart from the fundamental image that we're interested in. And this, this happens in any sample, but it mostly becomes more apparent and prominent in thicker samples and also just like stronger phase objects. So there are ways to eliminate these ghosts, either through image processing methods so that we can process them, or we can also make modifications in the hardware to address this. So in our current configuration with the laser faceplate, we can adjust the polarization of the laser light with some compromises to the cut-on frequency for our faceplate. An alternative approach is a crossed laser faceplate. And so in that case, we actually put two cavity arms perpendicular to each other, interacting with the electron beam. And there are benefits to such a system. One is there's an additional boost in the low frequency contrast that we can obtain. And in addition, there's a ghost suppression in some sense. So in a single laser faceplate configuration, we get ghosts on either side of this fundamental image that we're interested in. With the cross faceplate, we actually get, because it's a 2D grading now, we actually get more ghosts, but each ghost is reduced in intensity. So, experimentally, we don't know yet, but it is possible that this configuration would make it more viable for reconstruction and not having to do post-processing with the imaging. So this, we have some theoretical calculations of this system out on arXiv, and we're also working with Chan Zuckerberg Imaging Institute in Redwood City, where they've hired an engineering firm to design such a system. And so, yeah, that's sort of the next generation faceplate that we're working on. Before I end, I'd just like to throw out another sort of like this. We're working towards more biologically relevant samples. So this was also on the Titan. Also pretty recently, we've imaged some VLPs, and you can really see that these proteins really just pop out. We haven't done any processing on these yet, but stay tuned. So for that, I like to conclude and provide a bit of an outlook. So I'm really excited that our laser faceplate, we've installed a new laser faceplate on our new microscope Thea, and we can routinely perform single particle analysis and tomography data acquisition with the LPP in both our systems. And we're really at a point where we can explore the full capabilities of an LPP, trying to understand, what sorts of sample can really benefit from the laser faceplate, what sorts of new software or, things to make use of the low frequency information might be nice. And we're poised for biological applications. And hardware development, I mentioned we're working with CZII on the cross faceplate and equipping their microscope with the faceplate. And we're also working with Thermo Fisher to transfer the technology and make it available to the community. With that, I'd like to thank the team. Our PI, Holger Mueller, and also Bob Glazer has played an important role in developing the faceplate. And this is our current team. And thank you for your attention, and I'm happy to take questions.
Thank you very much, Jessie. Please, questions from auditorium, and yes, please. And while we're delivering microphone, there is a quick question from Slack channel from Sonia Welsh. Exciting, the faceplate setup with this electronics optics appears to be much smaller on a new microscope, and it seems to be conveniently fit into the enclosure. Is that impression correct?
Yes. So, well, the optics fits in the enclosure, but we put the electronics outside just to not have so much EMI and interference and things like that. Yeah.
Thank you.
Hi, thank you. Could you please tell us more about the relationship between the laser faceplate and the voltage of a microscope? Can we use 100 kV in the future and not 300 kV?
So 100, so lower voltages would, so sorry, let me rephrase that. So we can get the same phase shift with a lower laser intensity at lower voltages, but the cut-on frequencies are also kind of different. Yeah. But it's definitely doable, yeah. But the benefits that you get from that, I guess there are still trade-offs.
Thank you. More questions, please.
So maybe I missed this one. So I was wondering, your B factor comparison. So the B factor is a property of the sample. So I wonder actually why you had different B factors with phase factor on and off. And also I wonder actually, so given the differences in the B factor where you get the lower B factor when the laser is on, so does that mean the scattered beam has the more high frequency signal?
So I guess there are two parts to that. So the first part, I would say that the microscope aberration plays a part in the B factor. And so that's why we see the difference. It sort of depends on how you define that, but like aggregate on aggregate, that's what we see. And the laser on, laser off comparison, those are both with the transfer optics on. And in that case, the B factor is really comparable. There's a slight offset, which we don't fully understand. It could be sort of the orientation estimates being slightly different, but I would say those are comparable. So there's no difference in those two. Does that answer your question? Okay.
Thank you. There is another question, and maybe as the microphone again has been delivered, I'll ask a question from Slack. Question from Julia Zanetti. For a single particle, would it be possible to, or is it easy to switch the transfer optics on and off to collect pairs of images to use for low and high resolution, like an old-fashioned local pairs?
So yeah, that's actually a really good question. So turning the whole transfer optics on and off, there are, I guess, like it's more practical issues in terms of like hysteresis and things like that. So you'd sort of need to realign the microscope in some cases. But you could just turn the laser on and off, and that is something we're working on. So that sort of involves some of the laser electronics and the cavity mechanics.
Yeah, but that will switch off the ghost images.
Yes, but it would also be like no faceplate, but yeah, you can.
Thank you.
That's a good
We
question.
have probably time for a couple more questions. So over
Yeah.
there. And
So very exciting results. I just had a very naive question if you've tested the laser faceplate on different thicknesses of samples and how it performs when the sample gets thicker.
That's a fair, we have not systematically. So are you saying like you might think that with different thicknesses it would perform different? Like
I mean, that's the
independent of
question. Like, does thickness of the sample degrade the performance of the
right?
faceplate? And to what extent it would?
I see. We have not, but we could look into that. Yeah.
last question.
Yeah, I just keep staring the ghost images. So those are gold bits, obviously you're easy to see them. So they're also supposed to be everywhere in the single particle projection images. But when I look at the tomogram slices, the gold is the ghost image appears on the different height compared to the real image. So why is that?
So the issue with ghosts in tomography especially is because when we tilt the sample, the ghosts are still a fixed distance apart in the image. So it doesn't follow with the tilt. So that's why it's thinking it's somewhere else. So if the ghosts also scaled to the cosine or sine of the tilt, then you wouldn't see this. If that makes sense.
Okay, one more question then, and we'll maybe you can.
Could you use a mode-locked laser, which just sends a train of pulses? They are very intensive and equal in distance. And then you get, when you make a movie, both images at the same time.
And you're saying just like not with a cavity. You're saying just like a pulse laser.
With a cavity or without? I don't.
Right. So it depends. Are you saying you want like both the laser on and off data? I suppose we could, but it depends on like the width of the pulses. So we're. Yeah. So that is a possibility. Yeah. Mm-hmm.
Follow up on the, so laser grading creates ghosts.
Uh-huh.
And then laser grading distance depend on the laser frequency.
Right.
So you can you find the range of frequencies that it's not as drastic, far apart doesn't come into the play.
Like try to make the ghost really far away. Yeah. That's a good point, but unfortunately it's sort of limited by, let me see, this. And we don't have much choice over the laser wavelength, and also the objective length is kind of fixed by the microscope. So, but
Thank you very much. Our next speaker, I will introduce. Thank you, Jessie.